meeting is being recorded.
Okay, yes, welcome everybody now to the, not the start of the class, but the interesting, fun part of class, not quiz part of class. Those of you who like killing trees, there is paper up here for you to contribute to that. And we have three quick announcements for today. First one is your PageRank assignment has been graded and entered in Sakai. If you do not get full credit for some reason, then there's a note in Sakai explaining why. A handful of people, there was some sort of, I couldn't understand the submission somehow, and you got a 0, but it's just a temporary 0. Told you what to do to fix it, to resubmit. Do that and send me an email once you've done that, and I will regrade the assignment for you. There's another homework, a new homework that has been posted into this finite hypothesis classes folder in the topic 2, learning from data part. We will go over that today, what you need to do for that today. Not at the beginning though, sometime middle, endish of class, we'll go over this assignment right here. You'll definitely have everything that you need for this assignment by the end of class today. So I was originally going to make the assignment due this coming Sunday, but I've decided to extend it till next Sunday, October 13th at midnight. My sense is that this assignment right here will be a little bit easier than the PageRank assignment. Then last announcement thing, you'll have another quiz on the quiz2practice.pdf file that's also in this folder next Wednesday, a week from today. It'll be 4 true-false open problems, and the quiz itself looks something like this. Same sort of format as we had before about PageRank, but now it's on the stuff from Chapter 1. And there's also a key over here that marks down what the correct answers are for these. It is possible that I've made some mistakes in the key here because there's a lot of copying and pasting going on that I was doing, so I might have accidentally copied and pasted the wrong things here. I guess my sense that I think there's 15 problems here, probably 14 of them are labeled correct and probably have a mistake somewhere. So I don't know of a mistake, but there might be one. Again, that quiz a week from today, and my hope is that, where are we going? My hope is that this finite hypothesis class is homework, along with those different notes packets, prepare you for the quiz. Any questions on anything administrative about what's upcoming in this class? Okay. Then let's get to the meat of class today. Fun technical stuff. So we're in this between chapters 1 and 2 notes. This is the notes3.pdf file in the topic 2 section. And again, the reason why we have this set of notes is the difficulty in mathematical sophistication jumps quite a bit between chapters 1 and 2. And the main purpose of this set of notes here is to help you get more comfortable with some of this notation mathematically. And that'll also be the main purpose of your programming assignments, just really trying to help you understand like all the different notation here in these hypothesis classes, for example. Last time we drew a bunch of these hypothesis classes and talked about the size of those hypothesis classes. Really, the size is the one thing that you absolutely have to be able to understand about these finite hypothesis classes is how to calculate the size. And in particular, for these 5 examples here, what is the size? And then we also talked about there's this try everything algorithm that the most obvious thing to do if you have a finite number of possible functions. Again, a hypothesis is a synonym for a function in the context of machine learning. If you have a finite number of functions that you might possibly be considering, then one thing you could do is try them all and take the one that is the best. And that is this try everything algorithm T right here. And last time we talked about how the runtime for this, or what the runtime for this is. Again, one of the things that you will need to be able to do for any algorithm, we'll be discussing many algorithms in this course, but for any algorithm is talking about the runtime. Let's go through, I'm going to go ahead and review that real quick. What is the runtime here? We have the obvious thing here that is slowing us down. Our runtime here is this for loop here, and for H in capital H. So for every hypothesis in our hypothesis class, big H right here, we're going to do this for loop, and we're using the letter M in the textbook. M is the number of elements in a hypothesis class. Again, N for the number of elements in the data set, M for the number of elements in a hypothesis class. So this loop will happen M times. And there's some hidden runtimes here that are maybe not quite so obvious, like this En of H right here. Recall from your quiz just a couple minutes ago that that is defined as 1 over n times the sum from I equals 1 to n of a bunch of stuff. The important thing right now is that this is a sum, so like a for loop happening n times. And so last time we said that the overall runtime of this is going to be O of Mn, or even more accurately, theta of Mn. And in particular, this is the number of times we're going to have to call the base hypothesis. Number of times calling H. Because maybe I will write out the stuff in here. There's something like H of X sub I not equal to Y sub I. Each one of these iterations inside the sum here, calling that H. So theta of Mn times calling H right there. And we talked about, okay, you can't do this on something like the perceptron algorithm, which is an infinite hypothesis class, because for the perceptron, we have M is infinity, and so the runtime would be infinite, and it would never terminate, so that's bad. So this only works for the finite hypothesis classes. And then we finished up last time talking about this problem 4 right here, where I drew a big chart, and we're going to do that chart again in a second. This time, though, we will do it in the context of the finite hypothesis class generalization theorem right here. Any questions about, so we're going to start here talking about this theorem here in just a second. Any questions about where we are or what's going on? Okay. So the finite hypothesis class generalization theorem. This is something that is not explicitly stated as a theorem in the textbook. It's just given as like a couple of equations in the middle of the text, but I've pulled it out here and stated it as a theorem so that it is easier for us to refer to when we're talking about things. And again, this discussion about this concept, this theorem, pages 40 to 41 on the textbook. The most important thing here for us to observe is that this theorem looks very, very similar to the Hoeffding inequality. The only difference about this theorem and the Hoeffding inequality is this M value right here. Only difference between this and the Hoeffding inequality, between this and Hoeffding, H-O-E-F-F-D-I-N-G. And again, I did not put the Hoeffding inequality on your quiz that was today. That was I guess a slight mistake on my part. I had intended to, I wish I had, but you're not expected to have that memorized at this point. But you will soon have a quiz where you have to have the Hoeffding inequality memorized. You'll also have to have this finite hypothesis class generalization theorem memorized, and several other theorems that all follow the same exact format that just have some minor like change between the different theorems. And so the one tool in your toolbox for aiding in that memorization is like memorizing the diff between those theorems. What's different about them? And it's this M right here is the key difference between Hoeffding and this theorem right here. This is how the book states the equation for this result. If you redo a bunch of math, though, you get this thing down here, which is entirely equivalent. And this is the version that is most useful. So most useful version. Most useful. Again, like when memorizing the statements of these theorems, these two things entirely equivalent to each other mathematically. And it's just a matter of rearranging terms. And so it's useful to go through that step of rearranging terms for yourself once to be comfortable with the fact that they are the same thing. But after that, just memorizing it. And again, they fall into a pattern here. And what this is saying here is that the difference between our E out, so our out of sample error, this is the thing that we care about. Again, E out is the most important quantity in machine learning. But unfortunately, we cannot measure that directly. The difference between E out and E in is this bound right here. This is a useful inequality for us because E in is something that we can measure directly. Our in sample error is something that we have access to. It's something that we compute in the middle of this T algorithm, for example. And essentially, every machine learning algorithm is going to compute this as a step of the algorithm somehow. So E in is something that's always available to us, always easy to have. And this quantity over here tells us some bound on how bad the quantity that we really care about can be. This bound, the important parts over here, the thing to actually make sure that you remember is the following version. So E out less than or equal to E in, those parts being the same. And then I'll write in big O notation over here, 1 over in, and I'll actually change this one to a log of m over n like that. The relationship that people care about that we're going to be using in our applications is the relationship of m right here. Change colors. And again, the size of our hypothesis class to n the number of data points. And in this case, what I have suppressed is the probability. This statement up here says that this holds with probability at least 1 minus delta. So this is true with probability at least 1 minus delta. Delta is going to be a small number appearing in the log down here. And that probability part's not going to be important for us. Statistician people care about those probabilities. Again, the probabilities, these deltas and these epsilons related to confidence intervals. We talked about that a little bit with the Hufting inequality. But machine learning people, data mining people, we don't really care about the deltas and the epsilons in practice. We don't use them for anything other than the statements of the theorems, the proofs. What we actually use to determine our problems are the other variables here, the m value and the n value in this case. And so this is the relationship to fully memorize, or to ensure that you can't pass the class without having this part down. And I forgot the square root right here in the outer part there. So there should be square root log m divided by n. Couple things to jump out here. The first thing that jumps out to me is anytime I see a log in an equation, that strikes me as something that is fantastically good. Logs are amazing. Exponential improvement is amazing. Logs are amazing. And so this is fantastic that we're logarithmic in the size of m over here. Okay, let's see. So I said too that we're going to talk about this version of the equation in terms of the chart down here. So let's go ahead and do that. I'm going to scroll down and I'm going to redraw this chart explaining the same sort of things that I explained at the end of last class last time, but now focusing it on relating it to this equation right here. Again, the x-axis of what we drew last time down here is our model complexity. Model complexity. We're going to have many different measures of model complexity in the remainder of this semester. At this point, our only measure of model complexity is this m value, the size of the hypothesis class. On the left-hand side, we have low, and so approximately equal to 0. And on the right-hand side, we have high, which is the limit as m goes to infinity. Really, really big values. And we started by talking about how the training error is going to go down as you have a more complex model. Then your training error, E sub n, is going to go down. As you add more things into your hypothesis class, then your the possibility that you'll have a function that matches your training set is going to increase, and so your training error is going to go down. This is going to be one of the trends that you will observe on your homework assignment, and so hopefully the assignment will make this discussion here a little bit more concrete. But again, the thing that we actually care about is not our in-sample error. The thing we actually care about is our out-of-sample error. And we now have this bound on this generalization error, E out less than or equal to E in. That's equivalent to saying E out minus E in. Our generalization error concept is equal to O of log of m divided by n, like that. All I've done is rearrange the term. So E in here is on the left-hand side. And this is our generalization error. We defined that term last class, maybe 2 classes ago. And we can see that for a fixed value of n, if n stays constant, the m value over here, the complexity measure, is going to get larger. And so our generalization error is going to get larger. As m gets larger, our generalization error gets larger. So this is our generalization error. Generalization error. There's no particular fancy symbol for generalization error. They just write out generalization error everywhere in the textbook, and that again is the E in minus the E out. Other textbooks, other authors consider the out of sample error, E out, to be the generalization error, but for our purposes, generalization error is this difference. And using these two things, we can figure out that the out of sample error is the sum of these two quantities. The E out is E in plus the E in minus E out right here. And so this gives us something that looks like this, where in the middle, not necessarily where the points cross, but somewhere in the middle, we will have our best possible model right here. This is our best model right there. Yeah. Our best model, and in particular, these are all different points on this x-axis are different hypothesis classes. So our best model / H / hypothesis class, all sort of synonyms for each other in this context. Hypothesis class, like that. And this up here is the E out. And our goal again is to minimize this E out to get the best possible out of sample error, the best possible performance on data that we have not yet seen. The bounds, like this one up here, these theorems, the reason we're doing these bounds, the reason we're going to see a lot of them is so that we can relate this E in, this in sample error, to our E out, our out of sample error. Any questions so far about any of that? Yes.
On the, like when you scroll up, do you mean to do E out minus E in?
In the pink here is the question is, should it be E out minus E in or E in minus E out? Yeah. Let's see. So the question is here, does the order of these terms matter? And the answer is that so there's a couple levels of answers. One of them is that because I put the absolute value around here of the E out minus E in, the order is not going to matter just from a literal mathematics standpoint, because you can multiply it by a -1 and it's still going to have the same magnitude. So in that literal standpoint, the order doesn't matter. It also turns out that if I take away the absolute value bars over here, then the order still won't matter, because again, the big O over here is an upper bound. And so if this goes negative, then it doesn't matter how negative it goes, it's still going to be upper bounded by something positive. This thing over here is positive. So it's not going to matter for two reasons, the order of these terms. The textbook, when they talk about generalization error, they might do E in minus E out, E in minus E out. But these two things, these two quantities are always going to be the same as each other. Maybe aesthetically, E in minus E out, some people might prefer that because E in will typically be larger. E out will typically be larger than E in. So that's why tend to write it this way, but either way is correct. Did that answer your question? Yes, Hamika. Yes, so that should be a square root. Thank you, right here. There, Kevin?
I missed this earlier, but how do you go from an inequality to a
The question is, up here I have a less than or equals to, and down here I have an equals. And how did I do that? The answer is that it's the inequality up here is hidden in this big O notation because the big O by itself is only an upper bound. It is not a theta, for example. If these were thetas over here, then I would not be able to go from the less than or equal to an equal sign. But because it's a big O, it's just an upper bound on this range over here. And so whether I put an equals or a less than or equals to is semantically the same thing. Good question. Let's see. Yes?
So why do you want the E out to be close to E in?
Question is, why do we care about E out being close to E in? And that's a great question. These are the kind of questions that you should be asking yourself every time we see different theorems about different things, is like, why do we care? And the answer here is that, so the question, why do we care about the generalization error? Why do we care about that being small? The answer is that ultimately the thing we care about, the only thing we care about ultimately is our out of sample error E out. And unfortunately, it's something that we cannot calculate directly. The only thing that we can calculate directly is the in-sample error E in. And so chapter 2, the whole purpose of chapter 2 is to come up with some different bounds on the generalization error E in minus E out. And in doing so, we can relate E in to E out and come up with an idea on how good our E out is going to be. We'll see later on in the middle of chapter 2 that there are some, you can use this to determine which model you should use to solve different problems, or seeing the applications of this maybe more concretely. But the first sort of level of this answer is that we care about E out. The only thing that we have access to is E in. So in order to understand E out, we have to understand this generalization error to relate E in to E out. Yes, Joe.
Could you go back to the equation pseudocode for the algorithm?
Yeah.
So when we're finding E in, I was looking at this, it looks like as this iterates E in the case. Is that right?
Let's see. Okay, yeah, so I wrote this when I wrote the pseudocode here as doing it in terms of accuracy instead of error, that we're starting off with negative infinity, and then when we find something bigger, we replace it. The accuracy is 1 minus the error. So you can, yeah, the actual, I guess right here, this is a typo, that should be 1 minus the E in right there, or alternatively starting at positive infinity and replacing things when they get smaller. Yes, so I believe you have identified a typo here in the code of this algorithm. Did that answer your question? Cool. Thank you for pointing that out. So this is going to be something that you'll have to implement in the homework assignment. So let's go ahead and switch gears over here to talk a little bit about the homework assignments. The homework assignment is in this folder, Finite Hypothesis class, inside of the Topic 2 folder, and it is a IPython notebook. And it looks like I accidentally closed my IPython notebook. I will restart it for us for a second. And there are lots of ways to start and interact with IPython notebooks. VS Code has its own special things. I use the terminal. However you do it is fine. The purpose here of this assignment, big picture idea, is you're going to be using these finite hypothesis classes to solve the MNIST problem. MNIST, we talked about it the first day of class, haven't talked about it since then, but it's this data set where you have a bunch of handwritten digits and you want to figure out, make a program that automatically determines for you what the number or what the actual letter number is of the image of that handwritten digit. With these simple finite hypothesis classes, you'll be able to get about 90% accuracy on this problem. After we're done talking about everything in the textbook here, you'll get state-of-the-art accuracy of greater than 99% on this problem. Oops. Maybe as an aside here, there's lots of things that I don't like about IPython notebooks. One of them is what just happened. If I click on something, it takes me away from it. More broadly, though, is IPython notebooks encourage a lot of bad programming habits. And so I try in vast majority of my classes not to touch IPython notebooks. But people do use them a lot for data mining, machine learning applications. So I feel obligated to have at least one or two of these in this course. Instructions here. I need to learn not to click. Instructions here. There's 5 parts of this assignment, starting at part 0. 3 of those parts, 1, 3, and 4, have a fix me annotation inside of them that you will have to fix. The first fix me annotation here is in this hypothesis classes. I, at the top here, explain how to implement various hypothesis classes in Python. And then I provide for you the H-binary and H-axis hypothesis class. You'll have to implement the next 3. So that's the first thing to fix there. The next one, okay, just loading the MNIST data set. There's nothing to fix in this part. Just look at some pretty pictures of what our data set looks like. There's some 1s and 2s. The model training over here, there's this T class right here. You'll have to implement the fit method right here. This is that pseudocode that we were just looking at from the notes. This is the hardest part, I think, of the assignment, but it's only like 5 lines of code, so it's not that hard. The important observation at this point is that in scikit-learn, every learning model has 3 functions inside of it: a constructor, a fit method, and a predict method. And so the code that you are writing right here is fully compatible with everything inside of scikit-learn. The different comments here explain some more details about that. And then the last thing down here, there's this section on random projections, and this is getting into the most interesting part of the assignment programming-wise, and the most interesting part of the math in the notes packet. And this is going to explore some trade-offs for you about the different hypothesis classes. One thing to observe here is, so a random projection is taking one of these large images and compressing it down to just a small number of pixels. Here, the example where it starts with is taking it down to just 5 dimensions. And you can see here that this is what those original 1s and 2s looks like in 5 dimensions. A human cannot easily interpret what's going on here. I no longer know whether these are supposed to be 1s or 2s, but you'll see that your code that you're writing is basically just as good on this 5-dimensional problem right here as this. Turns out this is 784-dimensional problem. Where'd they go? The 784 dimensions. Your code will be just as good on the small dimensional problem as the big dimensional problem, and you can make it a lot faster by working on the small dimensions. So there'll be some things to implement down here as well. I want us to, in the notes packet, scroll down to the very bottom page, and let's see, yes. This is the part that talks about the random projection here, and the last part of the homework assignment is related to problem 8 here. So this is part 4 of the homework. Okay. So the idea here of this problem and the homework is that we're taking some large dimensional data points and making them smaller dimensional. there's going to be a matrix A that will do that for us, and A is this D prime by D dimensional matrix. Again, recall that X in this textbook is always contained in R to the D. The dimension of our problem is always determined by the X variables, by our input data points. And this A is just going to shrink that from D dimensions to D prime. In the what we were just looking at, D prime was equal to 5. So shrinking it drastically down into a very small amount of data points. And there's a table right here that goes through the runtime of the T algorithm on these 5 different hypothesis classes and the corresponding generalization error on these 5 different hypothesis classes. And I'm going to work through at least the first 2 here as examples so that you can get a sense of why this is important. So scrolling back up to the pseudocode where we talked about the runtime of the T algorithm, we can see that the runtime again is theta of m times n, theta of m times n. So I'll write that for us down right here. The runtime of T is theta of mn. And so the important thing here is for us to know, like, how big is m going to be for each of these hypothesis classes. Again, m is the size of the hypothesis class. We said before for H binary that m equals 2. And so the runtime of T on H binary is constant independent of the dimension. Plugging in 2 for m right here just gives us n. So runtime of theta n. We just have to visit every data point exactly once. The h-axis over here is different. We said that the m value for that is equal to d. And so the runtime for the T algorithm on the h-axis hypothesis class is theta of d times n. And so now we can see that this random projection up here is going to affect the runtime of the h-axis hypothesis class, but not the h-binary hypothesis class, because h-binary is independent of the number of dimensions, and h-axis is dependent on the number of dimensions right here. Maybe I'll to add a little prime to this D because it's specifically saying what's the runtime after doing this transformation, where our data points have D prime dimension instead of D dimension. So this is our runtime issues over here, our generalization error of H binary. So we said that the generalization error O of log M, maybe I'll write the original thing up here, O of log M divided by n. Again, when we're just thinking about this in terms of how to determine, like, comparing algorithms between each other, it's convenient to forget about the deltas and epsilons and the probability stuff and just think about what is it in average, and that is log m divided by n. Here the m is a constant, so, and I keep forgetting the square root today here. That's all inside of a square root. So the generalization error of H binary is going to be square root of 1 divided by n, like that. For the h-axis, though, the generalization error, m being equal to d, we'll get O of square root log d divided by n, like this. And this is, again, this log, very, very powerful here, that the generalization error is basically unaffected by the number of dimensions that we have. We can make D very large, so the full data set, 784, and the log of that is still a very small number. It's going to be like 3-ish. And so our generalization error will stay low, and so our out-of-sample error will stay low here with this bound. The other 3 hypothesis classes down here, I'll have you guys do those on your own, but you'll see some trends about, or the purpose of the homework is to see that you'll see some theory results here, and you'll see those actually replicated in practice in the homework assignments. Yes, go ahead, Elvika. Question is, why do I have a D prime right here? I guess I should be making all of these D prime for consistency. Question is, where is D prime coming from? The answer is that the purpose of this random projection is to take a big picture, like an actual picture of, take an actual picture of a handwritten digit like this, and project it down into a smaller dimension. So these data points right here are 784 dimensional, and we project that down into a smaller 5 dimension. So the d prime over here in this case is 5. And the way that we got this new data point right here is by the by this equation right here, just multiplying by this random matrix A.
So this is just a little question, but something like the vectors, it's like how much of each other in that one pixel?
So interpreting these new pixels is not, there's not really a meaningful semantic interpretation of these pixels. It's just, this is our new data point, and we throw it in the algorithm. We know that the algorithms obey these properties, and so we'll be able to select which one of these algorithms to use over here. We'll be able to select which one of these algorithms to use based on these properties. What you'll end up seeing is that the multi-axis 3 here has the worst computational runtime, and in fact, it won't finish on the largest data set, and so you'll so you can't actually use it, even though it has the best statistical properties, or maybe still has good statistical properties. But because it's the worst over here, you will not be able to use it on the problem. Worst, so can't use for the large d prime values. I don't know if that actually answered your question. I forget what your question was. Okay. Again, so there's a little bit of implementation stuff that you'll have to do in this homework assignment. But really the focus of this is trying to understand the relationship between these hypothesis classes, and how do you choose which hypothesis class to use based on these different properties that we can prove about those hypothesis classes. Again, in chapter 2, we're starting to talk about these infinite hypothesis classes, which are much more powerful than these ones here, much more effective. And those ones I will not ask you to implement at all. Those ones you will use the scikit-learn implementation. But we will have a similar set of runtime and statistical properties that we'll use to take advantage of, or to determine which algorithms to use. Let's see. Probably this is, people have maybe sort of vague questions in your head about what to do because you haven't looked at the homework yet. I think reading through the homework will hopefully answer those questions. Let's go ahead. We're doing good on time right now, so let's go ahead and do problem 6 right here in class, instead of having you all do it on your own. So this problem 6 is one of the sorts of things that we want to be able to think about and about with hypothesis classes, and it will help us reason about how to choose different models. So here we have given 2 finite hypothesis classes, H1 and H2. We can construct a third hypothesis class by unioning those 2 hypothesis classes together. So previously, I gave you 5 examples of concrete hypothesis classes with a particular formula, but we can now construct, out of those 5, another couple dozen hypothesis classes by taking various combinations of unions of those hypothesis classes. And this question is about, like, what can we say about the statistical properties of those hypothesis classes? So here, let G sub I be the result of the T algorithm on hypothesis class H sub I. So with this first sentence here, what it's saying is, as an example, G1 would be equal to the T algorithm on H sub 1. G2 is the T algorithm on H sub 2. And G3 is the T algorithm on H sub 3. So it's just being a little bit more generic with that, with the subscript right here, I, so that I didn't have to write out all three of these things explicitly. And then the question is, how does the in-sample error of G3 compare to the in-sample errors of G1 and G2? So the question is, E sub in of G3, is that going to be less than or equal to, or that's greater than or equal to, less than or equal to, or equal to the in-sample error of, say, G1? And this is the sort of problem that with a little bit of practice, you'll be able to do in your head without thinking about, but requires a very clear understanding, a very clear memorization of all of these different definitions. Again, if I didn't classify these problems into trivial and non-trivial problems, but this would be the type of problem that I would call trivial because it's just about manipulating definitions and nothing else. So the first thing here, so E in of G sub 3. Well, we know that, let's compare, so comparing G1 and G sub 3. We know that G1 is contained inside of H1. And this is by definition of the T algorithm because the T algorithm selects some hypothesis in H sub 1. We also know that G1 is the arg minimum over the H in H sub 1 of the in-sample error of H. And again, this is by just the definition of what the T algorithm was trying to compute. And so now my claim is that for G3, let's go ahead and write out these same facts for G3. G3 is equal to the arg minimum of H in H3, E in of H, that G3, so because H1 here is a subset of H3, H1 is a subset of H3. I know that's the case because H3 is defined to be the union of H1 and 2. So every hypothesis that is contained in H1 must be in H3. So G1 contained in H1, this statement right here, that implies that G3 is contained also in hypothesis 3 because H1 is a subset of H3. And so when we were doing this argmin right here, considering that G1 is the best of all the possible hypotheses, this G1 here and all the hypotheses that were considered in this first red part up here that I'm trying to circle with my cursor without drawing, this G1 here considered some subset of hypotheses down here. This G3 over here, this argmin over here, considered every hypothesis up here in H1 because H1 is inside of G3. So because G3 is this argmin right here, considered all of the stuff up here of this argmin, and G3 is the smallest, we know that the in-sample error of G3 should be less than or equal to the in-sample error of G1. Again, the G3 right here considered going over everything in H3. H3 is equal to H1 union H2, so it considered everything in H1. It, in particular, considered this G1 hypothesis right here. The T algorithm of G3 of H3 considered a G1 in one of its steps, and it might have selected G1. If it didn't select G1, it's guaranteed to have selected something better than G1. So the EN G3 less than or equal to the EN of G1 right here. And so that's the relationship between their in-sample errors. This type, again, this is the type of reasoning that we'll want to be able to do on all of the different algorithms that we will be seeing to be able to compare that, the in-sample of error of this algorithm is guaranteed to be better than the in-sample error of another algorithm. In certain situations. Yeah, any questions about that? Go ahead. Okay. All right, first, any questions about this? Okay. About whatever.
Going into your questions, generally, could we maybe talk about how you can speak with, like, the what protection means within
So the question is, instead of about 6, instead of questions about problem 8, how is d prime created? And the answer is that d prime is one of these hyperparameters that's sort of like alpha or epsilon from the PageRank paper. And the problem, the Jupyter Notebook walks through some reasonings about why you might select one versus the other. This is just a set of formulas about, given a particular d prime, what are those formulas going to be? How is it actually like mechanically computed? How is the projection mechanically computed? It's just doing a matrix multiplication like this. So I feel like that doesn't answer the question that you really have, so that's my answer. Does that? Okay, go ahead, Angela.
So D prime is actually not related to D.
Question is D prime related to D? And it's an arbitrary choice, something specified by the user here.
So when we're calculating the runtime and the generalization error, we're going by D prime and not D.
So let's see. 3 classes ago now, we looked at a set of notes where there was a bunch of different transformations that you can do to a data set to before applying it to the perceptron algorithm. And what do those transformations, how do they affect the runtime of the perceptron algorithm? This is the same type of problem here where we have some sort of pre-processing that we are doing to the data set. The pre-processing, in this case, shrinking the number of dimensions from D down to D prime. And so the new data set, the primed data set, the one that we are working on, is of dimension D prime. And so when you're doing everything on the new data set, it is in relation to D prime instead of D. Anna? And first, and then, yeah.
I was gonna ask about problems.
Yeah.
So like you were saying, so we looked at the ensemble error G3 compared to G1, but then you would still get the same reasoning with comparing G3 to G2 because you would have also looked at G2 and G2 is the best in H1 and therefore G3 would either be G2 or one that's better. So it would either be G1, G2, or something that's even better.
Yeah, so the question is here, the question as written is specifically asking the in-sample errors of both G1 and G2. I only talked about G1, didn't talk about G2 at all. And but the same reasoning applies exactly for G2 as it does for G1. And so the same relationship here, En G3 less than or equal to En of G2 is also true. There's nothing we can say about the relationship between G1 and G2, only about G3 and G1 or G3 and G2. Angelina.
I wanted to ask a little further back. The graph of E into the generalization error. I wanted to ask why the generalization error increases with model complexity.
So the question is, why does generalization error increase with model complexity? The answer is, the first level of answer here is that is what this theorem is telling us in a big, complicated, fancy way. That ultimately our generalization error here, the sort of simplifying out the probabilistic part of the equation. This is our generalization error. E out minus En comes from these two terms right here. And so this square root part is our generalization error, the square root of log m over n. And the m value over here is our measure of complexity. When m is small, like this thing on the right-hand side goes to 0. And so our generalization error goes to 0, is small. And oops. When m is small right here, the generalization error is small, but when m is large, the generalization error is large, and that's what this graph here is trying to show. A deeper answer to that question is why does this depend on m in any way? And the answer is that this result right here comes immediately from applying the Hoeffding inequality and the what's called the union bound to the Hoeffding inequality. That's where this m comes from. But it's an immediate consequence to that statement. Does that answer your question? Okay. So all the stuff in this notes is the same stuff that is in the chapter 2 notes, but specialized, the discussion specialized to the finite hypothesis class case. The remaining 10-ish minutes of class, and next week we'll talk about chapter 2 in detail here. And the idea of chapter 2 is to talk about these generalization bounds in terms of the actual for hypothesis classes that we care more about. And in particular, so this right here is, again, just a restatement of the finite hypothesis class generalization theorem. We have log m on the top, n on the bottom, square root over here for our generalization error. And what we're going to talk about in chapter 2 is we want to replace this log m, replace this with something that is applicable for infinite dimensions. So replace this with something better. That something better is called the VC dimension. And this is a somehow better or more important measure of the size of a hypothesis class. The VC dimension is one way of talking about the size of a hypothesis class. And it will turn out that many infinite hypothesis classes have finite VC dimension, and that will allow us to have generalization bounds on these infinite hypothesis classes. There's something called the fundamental theorem of machine learning that states this property right down here, that the generalization error is bounded by the VC dimension divided by n, like this. So we're replacing like this term right here. The only difference between equation 2 and equation 1 is we've replaced log m in equation 1 with this dVC right here, the VC dimension. This is not quite what the textbook, what our textbook gets to. What our textbook does is something a little bit easier to prove, which is this down here. The difference between what our textbook does and the fundamental theorem of machine learning is an extra log n factor. That extra log n factor in practice, not super critical because we're comparing a log n on the numerator with an n on the denominator. The linear n is going to vastly dominate the log n. Again, in practice, like anytime you see logs, that means you can basically ignore the term that's inside of it. It's the things outside of the logs that really matter. So the textbook doesn't fully prove the fundamental theorem of machine learning, but it gets really, really close. For our purposes, when we start talking about the applications about how to use the VC dimension to determine whether to use one model versus the other, it's not going to matter which one of these two versions you use. But this top one is easier to remember, and so this will be the thing that I will mostly use when we start talking about applications. The Bulk of this set of notes, though, is introducing like this actual VC dimension and what it means, a lot of notation. And so bulk of chapter 2, bulk of what we'll talk about is basically just trying to define the VC dimension, define the VC dimension, and talk about why it is important. At this point, so for next week in class, we'll be going over chapter 2, so you should start reading it. You're responsible for everything in chapter 2, with the exception of there are a couple of proofs of theorems that contain this begin, safe, skip section, and so you're not responsible for the stuff that's inside of this safe, skip. Everything outside of that, though, you will be responsible for. Okay, so yeah, again, big picture motivation, what we did in the last notes packet, talking about finite hypothesis classes. Now we're going to infinite hypothesis classes. We'll have the same generalization bounds. We'll have similar pictures that look like this. And then once we have all that theory down, we will talk about why to actually use it in practice, how to use it in practice. Okay, so we're going to start here with an example and some definitions. So again, I've tried to make our notes follow the section numbering in the book as closely as possible so that you'll be able to pick up in the book things that you missed in class. And in class, the things that I'm going to be focusing on, again, are the things that will help you understand the reading in the textbook. So the first one of these definitions that is very awkward is this definition of a dichotomy. And a dichotomy is this is the syntax that the textbook uses for the dichotomy. This is standard syntax. Everybody uses this. And here we have our hypothesis class. And this over here is some particular data set. So that is some data set. And the notation, what this means is that for every hypothesis in that hypothesis class, so again, this set builder notation right here, this colon means that we're doing like a for loop on the thing on the right. For every one of these H's in the big H, we are going to create a tuple of length n. This thing right here, this is a vector or tuple, vector of length n. Each one of these H's is contained, again, H takes our X values into the set of -1, +1, -1, +1. And so this tuple, this vector right here is in particular a element of -1, +1 raised to the nth power. Again, we talked about this set exponentiation in the context of the finite hypothesis classes and this set builder notation in the context of those finite hypothesis classes. So we apply the H function here individually, one data point at a time, to every element in the data set. And then because this is a set right here, this is a set, so it implies that we're going to remove duplicates. And the thing that's going to be interesting to us about these dichotomies is how many of these duplicates get removed. Again, all of this notation stuff that I just explained, not mentioned in the textbook. The textbook's assuming that you're able to grasp this notation and just immediately starts going into the examples. Before I get to this example down here, any questions on the individual notation parts up here? What's going on? Okay, so we have then 4 data points. 2 sets of 4 data points right here. And our goal, our question here is, what are the dichotomies generated by H-axis hypothesis class on these 2 data sets? So these are 2-dimensional data sets right here. So H-axis with D = 2 is going to be equal to the set of x into the sine of x1 or x into the sine of x2. And so there are only two hypotheses for us to apply right here. There's only two hypotheses for us to apply right here. And so these dichotomies up here, h of x1, all of this crazy stuff, there's going to be just two elements in every dichotomy. So the size h-axis equals 2 implies the size of h-axis applied to the data set, no matter how big that data set is going to be equal to 2 as well. I'm getting that fact right here from this sort of for loop right here, this notation, that this set has one thing in it for every h. What are the elements of that? The elements are going to be four-dimensional, applying each one of these h's to these four data points up here. h1 is the sine of x1. So if we apply h1 to, let's see, I'll write it down here. No, I'll do it up here. The h1 right here, what is the h1 value? Plus 1, our sine of x sub 1 is plus 1 here, so we get plus 1, sine of x1 minus 1, sine of x1 plus 1, plus 1, sine of x1 minus 1. That is hard to read. Plus 1, minus 1, plus 1, minus 1. h2 is the sine of the other entry over here, plus 1, minus 1, minus 1, plus 1, minus 1, minus 1. And so these are the two elements of our dichotomy. These are the two elements of my dichotomy applied to this data set right here. Notice that these two elements are distinct. They're different from each other. And so the dichotomy on this first set is going to have two distinct elements inside of it. On this second set, when I apply h1 to each one of these four variables right here, I get plus 1, minus 1, plus 1, minus 1, same as before. And then when I apply h2 to those same data set down here, the right-hand column, extracting the right-hand column, I also get plus 1, minus 1, plus 1, minus 1. And now these two values are equal to each other. And so this set notation that removes duplicates is going to remove one of these entries from the dichotomy. So the size of the dichotomy up here, size of the dichotomy will be 2. Here the size will be 1 because we remove duplicates. Again, the purpose of this example to get you familiar with this notation, help build some intuition about that notation. Question?
Sorry, but this is something really obvious. Why is the size of dichotomy 2 and not?
Yes, this is important question, important thing to keep in mind. So the size of the dichotomy is the size of this set right here. And the number of elements in this set right here is, we're going to have one element for each h in our hypothesis class. The size of our hypothesis class h-axis is equal to 2 because our h-axis, plugging in d equals 2 right here, we're looping over I equals 1 and I equals 2. Again, square root of d equals the set of 1, 2. And we're looping over each of those 1, 2s, and we get the sine of 1, sine of 2. So sine of x equals 1, sine x2 right here. So those are the two entries of our hypothesis class. And we're looping over only 2 entries. So this set can have at most 2 entries inside of it. The reason why it seems like it might have 4 inside of it is because the dimension down here, the dimension of the element of the dichotomy is 4. Down here we have the entries of our dichotomy are vectors of length n, whose each element of that vector is either -1 or +1. And so it's -1 plus 1 to the n. N is equal to 4 over here. And so the dimension of our dichotomy is 4. But the total number of elements in the dichotomy is 2. So it's somehow kind of like we're transposing the dimensions and the number of elements here, swapping them around. It's not exactly a transpose, but we're swapping the dimensions and the number of elements. We're 15, 16 seconds over time here, so I will stop there. And if you have more questions about things, then happy to talk about those after class. Again, these things, you just have to read the textbook in order to fight with these things, struggle with them. And the purpose of what we're talking about in the class is to help get you to the point where you can read the textbook. And let me